Hello, everyone. Our bell ringer question today is, what is the condensed electron configuration for Y or yttrium? Take a moment, look at a periodic table, write some stuff down, and I hope your answer is krypton 5s2 4d1. So remember, when we write the condensed electron configuration, we find the closest previous a noble gas. We write that noble gas in square brackets, and then we write the valence electron configuration. Today, we are looking at reaction quotients and the equilibrium constant. So our learning objectives are, I can explain the law of chemical equilibrium, and I can determine the overall reaction quotient for a multi-step reaction. So yesterday, when we started looking at equilibrium, we looked at our equilibrium constant. We were looking at that, approaching that from a chemical kinetics perspective. But when equilibrium, the concept of equilibrium, was initially discovered, kinetics had not yet become a field of study in chemistry. So when there was a couple of Norwegian scientists that were originally working with and discovering equilibrium, when they discovered this idea, they actually were looking only at ratios of products to reactants. So through that, we come to the law of chemical equilibrium, or the law of mass action. So when a system reaches equilibrium at a given temperature, the ratio of quantities that make up the reaction quotient has a constant numerical value. That's a fancy way of talking about our reaction quotient. So again, we're just talking about the ratio of our products to our reactants at equilibrium. When we are at equilibrium, that ratio is going to be the same regardless of our starting quantities, regardless of whether or not we start with 100% pure product and that reaction has to reverse, regardless of whether or not we start with 100% pure reactant and that product has to go all the way to completion or not. When the system is at equilibrium for a given temperature, we will always see the same ratio of products to reactants, regardless of what our starting materials are. It's the ratio that's important. In order to look at the ratio, we're going to start talking about our reaction quotient, or Q. So for the given reaction, AA plus BB yields CC plus DD. This can be a forward or reverse reaction. The reaction quotient is the concentration of our products to the power of their stoichiometric coefficients divided by the product of our reactants to their stoichiometric coefficient powers. So unlike in chemical kinetics, when we are talking about the order of a reaction and the order of particular reactants within the reaction, those had to be determined experimentally. We had to look at experiments where we manipulated one variable and left the other constant, and then switched and manipulated the other variable and left our other reactants constant. And that was the only way that we could determine what our order was, and therefore what our power would be for that particular reactant. When we're looking at reaction quotients, we can determine the reaction quotient just by looking at a balanced chemical equation. So the power that any particular reactant or product is raised to is the stoichiometric coefficient of that particular reactant or product, of that molecule or element. And another cool thing that we're going to tie all of this together with, so we've been kind of marrying our kinetics with our equilibrium, and we're going to do that with one more step. At equilibrium, Q, or our ratio of products to reactants, is equal to our equilibrium constant, our K. So remember, K is the ratio of the rate of forward reaction to the rate of reverse reaction. At equilibrium, the rate of the forward and reverse reactions is equal to the ratio of products to reactants. So that was the simple part. We're going to get this a little bit more complex because Q, our reaction quotient, is based off of the balanced equation exactly as it is written. That means that there are several variations that we will see, and we're going to look at 4 main types of variations for how to write Q in different forms. And today we're going to focus on one. We'll cover the next 3 tomorrow. But the Q, or the reaction quotient, for an overall reaction is where we're going to start. So the reason that we need to think about the Q for an overall reaction is because when we look at a balanced equation, that balanced equation does not necessarily give us information about whether or not that is a multi-step reaction. And if it is a multi-step reaction, we need to consider all of the steps that lead us to our final product. So again, we need to think back to our chemical kinetics. We're still making those connections. But the Q for an overall reaction, so the quotient, the reaction quotient, or in this case, the equilibrium constant, is the product of the reaction quotients or equilibrium constants for each of the steps. So Q overall, our reaction quotient overall, is equal to the product of the reaction quotient for each of the steps in a multi-step reaction. Likewise, the equilibrium constant overall for the whole reaction is equal to the product of the equilibrium constant for each of the steps in that particular reaction. Let's look at an example of the reaction between H2 and Br2 to form HBr to demonstrate this. So we have 3 reaction steps. What we need to do is combine these 3 to determine our overall balanced equation, and then we need to demonstrate the product of each of the reaction quotients, so the reaction quotient for each step. When we multiply those all together, that we end up with the overall reaction quotient. It sounds like it's going to be a lot, it's going to be a few steps, but it's not going to be challenging because all this is a game of multiplying things, crossing out like terms, and comparing. Let's start by adding our equations together. So we're going to look for things that we can cancel out. Ooh. And I see no BRs or H2s to cancel out. I see 1, 2 lone Br gases to cancel out. I see 1 Hg gas there. And I see 2 HBRs. When we add all of this together, we have Br2 gas plus H2 gas yields 2 HBr. All right, so that means that we can now write our reaction quotient for the overall reaction. Remember, our reaction quotient, in this case it's going to be overall, is equal to our products to their coefficient power. So HBr to the second power divided by the concentration of each of our reactants to their coefficient powers. However, in this instance, since they both have a coefficient of 1, our overall reaction quotient is going to look like this. So when I am writing my reaction quotient for each of the individual steps, I'm going to need to keep track of those so that I can put them all and combine them all together to show that they are equal to the Q overall. So let's call this Q1, Q2, and Q3. Q1 is equal to Br squared, because we have 2Br, we raise to the power, the same power of our coefficient, divided by concentration of Br2. So that is Q1. Q2 our ratio of products to reactants for our second reaction is going to be HBr times H divided by concentration of Br times the concentration of H2, and finally Q3 is equal to the concentration of HBr divided by the concentration of H times the concentration of Br. So what I'm going to do is I'm going to write the three of these out so that I can multiply them together, cancel out like terms that are on opposite ends of the divisor bar, and we will see if we are able to demonstrate that when we multiply our ratios for each of the steps, we end up with the overall reaction quotient, or the overall ratio of products to reactants. Okay, so when I write out each of the reaction quotients for each step, so for step 1, step 2, step 3, Q1, Q2, Q3, this is what my formula looks like overall. So again, now that we're in this stage, what I need to do is I need to cancel things out that are on, like I said, that are dividends or divisors. And then I need to compare to see if I do, in fact, reach my Q overall, my ratio of products to reactants, as we determined in our very first step where we added all of these together. So let's go through. Br squared, I see 1 and 2 Brs. So if we multiply these two together, that would be like Br squared in the denominator. Therefore, we cancel it out in the numerator. I've got a Br here. I don't see that anywhere else. I've got an H2. Don't see that one anywhere else. I've got H and H that can be canceled out. I think I'm as set as I can be. So right now, when I simplify that and I make it look nice and tidy, what I have is I've got 2 HBRs that I'm multiplying in the numerator, which means that when I multiply them, they're going to be squared to the second power. So I have HBr to the second power divided by, I'm going to put the H2 first because I like to put hydrogens first. H2 times the concentration of Br2. All right, so now I can check against the initial Q overall, the initial reaction quotient that I had calculated in that very first step, and they match. So when you determine the reaction quotient for each step in a multi-step reaction, and then you multiply those reaction quotients together, you do see that that equals the Q overall, the reaction quotient for the overall reaction. All right, let's take a look at 2 practice problems, 17.12. So we're going to look at 2 examples. They're going to be very similar. Once you do the first one, I'll let you have a little bit more freedom on the second one to just check your answers as you go along. So we need to have a balanced equation, and then we need to plug things in. Let's balance this equation really quick. All right, so we've got 3 oxygen, but I've got 1 nitrogen and 2 nitrogen here. I'm going to start there. I'm going to place a 2 as a coefficient there. And I am, for the sake of tidiness, not including the states, but you should be including the states when you're writing these equations because, especially as you'll see tomorrow, the state of your reactants and products is important. So we've got 2 NO2 and 2 O3. Well, then we've got 2 4O, so that does not work. I'm going to place a coefficient of 2 here, perhaps, and that will mean I need to change that bad boy. Then I've got 4 6O and 6O, 4N, 4N. All right, so my balanced equation is going to look like this. 4NO plus O2 yields 2N2O3. Now when we come to the part where we're writing our actual reaction quotient, it's pretty simple. We're just going to write the ratio of our products to our reactants, being sure to raise those concentrations to the appropriate power, so they're the coefficients of those molecules. So our Q is going to be our products. So N2O3, the concentration of N2O3, raised to the second power because we have a coefficient of 2 right here. And that is divided by concentration of NO raised to the fourth power because we have a coefficient of 4 times concentration of O2. And there you have it, pretty simple. So remember, when we are writing these reaction quotients, this particular reaction quotient, because we've not specified that this is at equilibrium, this is simply the concentration of products, or the concentration, the ratio of the concentration of products to reactants at a given point in a reaction at a given temperature. Because we have not specified that this is at equilibrium, we're technically not worried about, we're not worried about equilibrium in this instance. But if we were specifying that we were writing the reaction quotient at equilibrium, we would have Q sub EQ, or Q for equilibrium. We write them the same way, especially when we're dealing just with concentrations, but it is important to know exactly what it is you're saying when you write an equation like this. All right, so we're going to do exactly the same thing here. What I suggest is this time that you pause the video in just a second, balance the equation on your own, check, press play, check to make sure you've balanced the equation correctly, pause the video again, write out the reaction quotient, and then play the video, make sure you've written your reaction quotient correctly. So we're looking at SF6 gas plus SO3 gas yields SO2F2 gas. Again, now would be a good time to pause the video, balance the equation, check in just a second. All right, so this is what your balanced equation should look like. SF6 plus 2 SO3 yields 3 SO2F2. We've got 3S over here, 3S here. We've got 6O, 6O, and we've got 6F. So all balanced up. Again, now would be a good time to pause the video, write the reaction quotient, and then play in just a second to double check and make sure you've written it correctly. So when you've written your reaction quotient, it should look like this. We've got our product, SO2F2 to the third power because of our coefficient of 3, divided by concentration of SF6 times the concentration of SO3 squared because of our coefficient of 2. And again, remember that because this is a reaction quotient and not necessarily a reaction quotient at equilibrium, this represents the ratio of products to reactants at a given point in time in a reaction at a particular temperature.